Hello and welcome to this special session of the FUELGAE project. I'm Cleo Grapidis with RTDS Group. We lead the dissemination, exploitation, and communication activities in the FUELGAE project, and we co-organize this special session within this conference in COS. And this workshop named Closing the Carbon Loop, Converting CO2 and Waste Streams into Scalable Zero Waste Advanced Fuels would like to cover some of the FUELGAE results as well as some of our sister project results. So we will have a series of scientific talks and we will close with a panel with 4 experts that I will moderate. My colleague, Silvia Morales de la Rosas from CSIC, who coordinates the FUELGAE project, and Yanis Penloglu from CES, one of our work package leaders, will moderate the scientific discussion, and I will see you back for the panel discussion.
Yeah, thank you. Thank you very much. So welcome everyone from my side as well. Good morning to this session of FUELGAE project. As Cleo said, I'm Yanis Penloglu. I'm a researcher in CERT. I would recommend to quickly proceed with the presentations. We have a really tough schedule to follow, and kindly ask all the speakers to keep their time, about 12 minutes of the presentation time, and in order to assign a couple of minutes for the questions. And of course, we have the panel discussion as well, but we need to keep the time. So quickly, let's start with the first presentation. It comes from the coordinator of FUELGAE. It's Silvia Morales de la Rosa, a researcher in CSIC. It coordinates the whole project. She will quickly present the project and give us some guidelines, brief discussion about the results. The project is 1 year before its end, so we are well progressed, but we have some things to do as well. So Silvia can discuss. So thank you.
Thank you, Yanis, for your kind presentation. Thank you for the rest of the partners involved in the organization of this workshop of FUELGAE project. And let's start with a brief introduction. Sorry. I need to. Sorry? Oh, okay. Okay, now. Well, I want to introduce with a brief presentation of our project. I am coordinator, the totally sustainable on-site and innovative technologies for advanced transport biofuels from microalgae. Next slide. I don't know what happened. I don't know. Well, now. FUELGAE project is a European project from the cluster 5, climate, energy and mobility. The goal was development of algae and renewable fuels of no biological origin. It's a research innovation action, and the budget is around 5 million euros. This project started in October in 2023. And the duration of this project is 4 years. Now we are in the last year. Well, next slide, please. Okay, I want to no, I don't know what happened. Yes. I want to introduce our consortium. We have partners from the academy, research and technological organization. We have 2 industries, different, and we have a small and medium enterprises and association in our consortium. In total, we are 12 partners from 6 different European countries. Next slide, please. Well, no, sorry, the previous. And what I say, the project is a research innovation action, And the last technologies, we have achieved their L5 and 6, typical of this kind of the project, and we have to the transition. All our main technologies validated in lab scale to validated all technologies in a relevant environmental. And now I will show you a video produced by one of the partners for RTDAs. Only is a short video of 2 minutes. Next slide. Okay. We can hear.
To combat this, the European Commission has set an ambitious target and created the European Green Deal Initiative, achieving zero emissions by 2050. To realize this vision, the European transport sector must transition to energy sources that produce minimum or zero CO2. Biofuels are important solutions to make fuels used in cars, aviation and shipping more sustainable. Microalgae emerge as a promising resource for biofuel production due to their rapid growth rate and unique ability to capture CO2, which can then be converted into biofuels. Until now, the application of microalgae has been limited by the high expenses associated with their cultivation and the extensive energy consumption for fuel production and upgrade. The FUELGAE project is developing innovative processes to grow microalgae for efficiently capturing industrial CO2 and converting it into advanced biofuels. Microalgae test plants will be installed at 2 industrial sites as a retrofitting solution, integrating a new photobioreactor to capture CO2 emissions from biorefineries and energy-intensive industries. Through the implementation of new methods and studying new technologies, this pioneering project aims to reduce energy consumption, ensuring the affordability and sustainability of biofuel production. This innovative biofuel will be analyzed to verify its possible application in road, aviation, and maritime transport, promising lower and even net zero CO2 emissions and lower energy consumption. The FUELGAE project is a collaborative effort by a consortium of 12 leading research and innovation institutions and SMEs and industries from 6 European countries, led by the Spanish National Research Council. FUELGAE, funded by the European Commission, is dedicated to advancing innovative solutions for a greener and more sustainable future in the transport sector.
Next slide. Okay. Well, as I say in the video, the main objective of this project is the conversion of different CO2 emissions from a biorefinery and an energy-intensive industry through the microalgae to produce different advanced biofuels. We are developing different technologies. First, we select different microalgae according to the needs of our industrial case study. We have 2 case studies. And the second one, we have built and designed a new pilot plant, a photobioreactor plant, and we will integrate it in this different infrastructure in 2 industrial sectors. And we develop new novelty and treatment to have developed these results and to produce special lipids and sugar to produce all the biofuels. We have been tested an innovative multifunctional catalytic upgrading system to produce all these different biofuels. And the biochar produced in this project, we will test it like a solar in agriculture land. And we have designed a new family of sensors integrated in this pilot plant in the process analytic techniques, and we developed a global digital twin of all these technologies. And at the end, we have studies of the LCA and techno-economic analysis to try to ensure that the final product will reduce the greenhouse gas emission, and to try that all these processes are economically viable. This is an overview, or it's a schematic overview of our project. You can see the two industrial companies. We have different qualities of CO2 emission. We will capture in our pilot plan. It's a modular pilot plan. We can move between all industries, and we try to produce different products and special different biofuels to different sectors, the RAD sector, aviation, and maritime sector. In the project, we have to produce bioethanol, biogas, biochar, biocrude, and advanced liquid fuels. And we have a lot of other activities, transversal activities, like dissemination, communication, exploitation, modeling, digital twin, studies of LCA, and techno-economic analysis. In this scheme, we are divided into study case. Next slide, please. Okay. The first case study, we have captured the CO2 of the bioethanol plant of second generation to produce polysaccharides, and this polysaccharide we will introduce another time to the biorefinery to produce bioethanol for third generation. And the remaining residues we have to use to produce biocrude by thermal liquefaction, and this biocrude we will convert in advanced liquid fuels. The biochar produces in the hydrothermal liquefaction we want to use for soil amendment. In the second case study, we will capture the CO2 from a steel plant. This quality of the CO2 is worse and very different, and for this reason we choose another species of microalgae, and we have to extract the lipids, and this lipid we will to convert by catalytic upgrading in advanced liquid fuels, and the residual rest of the biomass of microalgae we will convert in biogas for anaerobic digestion, and we will use for supply energy for the steel plant. Well, in this slide I showed you all the milestones around these 4 years. Now we are in the last year, in the month 33, and we are finalizing the optimization of the catalytic conversion to produce advanced liquid fuels. And so far, the rest of the milestone of the project we have achieved. And the big challenge is in this year, because in March of 2027 we had to finalize the design and testing of HTL and hydrotreatment scale in Greece. And in April 2027 we had to finalize the optimization of the bioethanol production and biogas production. And at the end of the July of 2027, we had to do the validation our pilot plan in Spain and in Romania in the different industries. So, in September, we had to summarize all the final results, and well, I want to thanks the European Union through the CINEA to funding this project. And I would like to, the next slide, please. Well, I would like to show you our website. If you have more information, you can introduce in our web and follow us in our social media or contact with all of us, with me or with the dissemination and communication partner. And that's all for me. Thank you very much for your kind attention.
Yeah, thank you. Thank you very much, Sylvia. So we have, I believe, 1 minute at least for a question from the audience. Anyone? Or even online, I guess, if anyone would like a question. If not, maybe I can ask a question. So going 3 years into the project and looking into the different technology components, like the production of microalgae or the fragmentation or all of that, which would you say that is the most challenging one for the scale-up?
Probably.
Yeah. Maybe, well, technologically wise or even economically wise, whatever you think is most important.
I think one of the most important things is the watering of the microalgae to produce lipids and sugars.
Okay.
Because you consume a lot of energy in these kind of technologies.
So it goes to the economics. Yeah.
Yes, for the economics and the consumption of the energy at the end, yes, it's very higher.
Especially for in hydrothermal
Liquefy.
don't need drying. But in case of extraction for lipid, you need high energy for drying.
For in the hydrothermal liquefaction?
No.
In the treatment.
In the other way.
Yes.
You extract lipids.
Yes.
Yes,
You have to
for
introduce.
this-
Well, depending on the treatment, we have now designed a novel treatment, very different at the typical. We are writing in a pattern, and one of the challenges of this treatment is we want to use the part of the water of the microalgae. And it's true that we consume a lot of energy in the extraction, but we try to do in one step the extraction of lipids and the content of the sugars.
Yeah, thank you.
Yeah, but it's true. It's a challenge.
What was your yield, oil yield, upgrading yield? You did hydrofining process to convert the oils to hydrocarbons fuels.
Yeah, well, we have two different production of biofuels for hydrotreatment by drying catalytic. One is from the lipids. You have to do the oxygenation of these lipids. And in the case we use biocrude, we have a higher content of nitrogen, and you have to do both process in
and
the same.
yield was very low.
Sorry to interrupt.
It's a challenge, but it's possible.
We are already maybe a good discussion for the coffee break. Yeah.
Thank you. Thank you very much. Now I would like to introduce to my colleague, the research, Janice Polplow. We have a presentation in advanced closed photobioreactor configuration for enabling scalable microalgae conversion for industrial CO2 into biofuel precursors. It's a research in CER, and all this work is developed in his institution.
Yeah, thank you. Thank you very much for the introduction. Yeah, I will quickly go through some slides. I guess that need some time. Yeah. Okay. So already some of the introductory slides are already covered, so I will not spend that much time in that. But I would like just to emphasize again the role of microalgae in all this CCU discussion. So capturing CO2, converting CO2. We're not saying here that microalgae will replace the technology for CCU, but it can be a complementary technology that can convert CO2 into biomass and then into biofuels, but not only biofuels. Well, our project here is focusing a lot on biofuels. So this is what we're developing. A lot of interesting advantages for microalgae. Probably everyone knows in this room and in the audience their advantages. They're photosynthetics organisms that can convert CO2 and light into biomass. They have larger efficiencies than plants, terrestrial plants, all of the photosynthetic organisms in Earth, and a great flexibility in their metabolism, so they can work autotrophically, heterotrophically, in many different mechanisms, and they can produce in different value chains, lipids, sugars, proteins, whatever, for different products and applications. Our focus is, of course, on biofuels because of the project. So many advantages, but there are also some barriers or disadvantages, if you like, on the implementation of these technologies, on the scale up as well. First, quickly on the advantages. So clearly the microalgae do not compete with the food production, and they can utilize CO2 coming from industries as flue gases. So this is the main objective of the project as well. They have large growth rates. They have also a very wide product portfolio, but still there are major barriers here, and I'm focusing more on the barriers that are relevant for the production system. So the photobioreactors that I will speak about a lot in these slides. So mass transfer limitations, scale-up challenges because of the light, because of the mixing, because of the transportation of gases, the path for light utilization, contaminations risks as well, if you'd like to keep your culture tolerant to these things. And of course, energy and cost constraints. This is relevant to the scale-up. Okay. So we will focus, as I said, to the photobioreactor itself. It was one of the first tasks of the project to select a photobioreactor for our case studies, as Sylvia described already. This is a list of the major issues to deal with and address from the different systems. The configuration itself affects a lot on the availability of the light, on the gas-liquid mass transfer, on the hydrogen dynamics, the temperature control, name it, whatever is relevant for an engineering task for a typical chemical reactor, they are all here. All these factors are here, and even more because we're speaking for biological systems, but for microbial systems. And so this comes to the contamination resistance as well. So in the project, we focused from day one on closed systems, so closed photobioreactors. So this is a big overview. There are many systems out there. Some of them are well advanced, like tubular systems, like airlift systems, or flat panel reactors. There are others that are emerging. We will speak a little bit about for all of them, but you can name many different types of reactors. I'm not bringing in the discussion today any raceway ponds or open systems, but of course they are important as well. Maybe they are more advanced than closed systems, especially for applications of lower value, like wastewater treatment, this kind of applications. But here we focus only on closed systems. So you will see some sketches and some real images of different reactors, tubular, airlift, flat panels, membrane, and other systems. Each one will have its own characteristics, and the performance depends, of course, on the configuration, but it is a combination of factors. So the species themselves are affecting the production and the efficiency, the operating conditions, the scale of operation, of course, and the target programs. I neglected to say that our project goes up to TRL 5, so we're speaking up to a pilot scale for this for this presentation. We're not seeing like a demo plant or even larger, but of course this is in future plans. So the scope is to evaluate the main process characteristics of each photobioreactor configuration, and discuss a little bit about our selection, but specifically for the needs of the two case studies that were discussed before. So I will quickly go through four different types of photobioreactors, starting with the tubular. Maybe it's the most common one and most well known. Major characteristics that they have high surface area to volume ratio, and they're really efficient in the conversion of illumination of light, and the continuous profile on the culture. The critical parameters here in this type of reactors is the flow velocity and the tube diameter and the gas injection strategy. So a lot of advantages here. So they are really suitable for large-scale systems. They have a modular scale-up profile. They have relatively low contamination risk, and it's already a well-established technology, but there are some disadvantages as well. So oxygen accumulates a lot, so you need degassing units in between different modules. Probably there are also some issues with cooling if you are performing, if you are producing microalgae outdoors in an area where the temperature could be like 35 or 40 degrees. Pretty much complex cleaning and maintenance, and of course high energy demand for the pumping and the recirculation of the systems. The second category is an air-driven photobioreactors. Here the gas injection is the key factor, the key driving factor for the operation of these reactors. It affects the mixing, the aeration, and with aeration we mean, of course, mainly the CO2 supply, but also oxygen stripping. So there is a dual mechanism here when supplying CO2, and there is circulation of liquid. All this happen because of the airflow. So the advantage is the really high gas liquid transfer coefficients, and low shear stresses. It's a pretty much simple mechanical design with lower maintenance requirements compared to the tubular systems. But again, disadvantages here. So there are clearly limitations in the light distribution, and you need to control really well the bubble size of these systems in order to have efficient mixing and transfer of CO2 and oxygen. Usually there are issues like dead zones or fouling systems, fouling issues on this kind of reactors. Third are flat panel systems. Again, here you need to provide some gas, some air for the mixing. So similar characteristics with air-driven. The main advantage here is the panel thickness. So it's the thickness is low. It's the path for the light to be able to be captured by the cells of microalgae. This is really low, so we can control really well the efficiency of light use, so that you can produce biomass in high concentrations and productivities. So it's suitable for pilot scale applications, and usually this is used for more high value applications, probably not for biofuels. Also, similar issues with the airlift systems are occurred, like fouling that can reduce the light penetration. You need, of course, to control really well your temperature and other parameters. The scaling comes probably in parallel systems, so modular systems in parallel, and usually they have higher capex and opex than the previous systems. And the fourth category are altogether some emerging technologies, so membrane photobioreactors, biofilm photobioreactors, internal illumination systems. All of that are under development, are emerging. Still, there are some steps behind the previous technologies, especially if you're trying to find commercial systems or systems that at least are in pilot level or more. So I combined the advantages and disadvantages of them. So in all these systems, you facilitate a lot of downstream processing, and so you can enhance biomass retention and recovery. But there are a lot of the disadvantages as well. So, for example, the membrane fouling is the first category, or how to control the biofilm, which is challenging a lot, and the complexity of all of these systems. And at the end, you end up with an increased complexity and cost for this type of systems. This is why I couldn't find actually images of large systems for that. But all of that is still the photobioreactor. Yeah, so it's like the system to produce biomass, but you still need to integrate this with CO2 capture. If you need the technology before that, you need to integrate a supplier for the nutrients, for the water, as it was discussed already. You need different technologies for downstream processing. So the photobioreactor is only one part of the technologies that can enable this biorefinery system in complex systems. Now we go beyond biofuels. You can go to food products, to feed products, to fertilizers, whatever you like. And of course, I only presented only a few designs and a few configurations. You can find very sophisticated designs about the reactors, going to conical, to pyramids, to whatever type you need. If you search the literature, there are a lot of work on that. In each case, you end up with the same issues: light availability, mass transfer issues, hydrodynamics, temperature control. These are the major things for me. So in each case, you need to select something. So trying to compare all these things, all the systems that we discussed, it is quite challenging to find and assign a high level or a low level or a medium level to these factors, to the light efficiency, to mass transfer, to scalability. So I'm sure that each one of you would assign different levels to that. So we did that in the perspective of the project. And the comment here, or the message here, is that there is no solution for each technology. So you need to comply with the needs of your technology and identify the best system for you. In our case, we identified for many reasons that an airlift tubular system would fit well to our needs, because we have a CO2-rich system. We focus on biofuel, so we needed to keep the capex at least at the lowest level we can. So we selected to merge the first two in an airlift tubular system, and this is the system we're working with. And before finishing, I would like to present here an open access issue we have in processes. This is quite some time open now, and actually the deadline is on next month, early next month, the 5th of July. But already it's quite successful special issue, because we have already 14 publications out there. They have already received more than 150 citations. Two manuscripts are under revision. We're expecting 2 or 3 more. At least at the end, I estimate about 18 to 20 papers. So this will be really successful, and it will be featured by the journal. I know I'm over the time as usual. So key takeaways, messages. So I guess that we all agree that microalgae are a promising platform for CO2 valorization, with all the challenges you can name. And photobioreactor is one of the main factors here. We identified the tubular and airlift systems suitable for FUELGAE for our project, but there are also advanced systems to consider going to the future, and going to maybe in applications of higher value. And of course, one thing is the photobioreactor, the other is the integration with all technologies and all the components. With that, I would like to thank you very much. Of course, the special thanks to the project itself, to Sylvia and all the colleagues here that are present. Yeah, thank you very much.
Thank you very much, Janis. We are a little later, but
I was sure,
one question very fast. I have a question. Is possible to install this kind of a pilot plan in the building, in the construction, there are some projects about this, but
Yes, yes, there are. You mean you mean like in not in industrial places? You mean like in simple buildings or yeah? I've seen some. Even I believe that there is a project in London, or there was a project in London that they installed something like this, like a curtain in front of the whole building. I don't know if it succeeded or not. I'm seeing a lot of projects like having one system in the room, and they present it like a tree or whatever, so capturing CO2, etc. If you search, you will find these systems. Or there are systems with photobioreactors like in buses in the cities, or like in solar. They call it like a bus stop with a solar on top, to a solar system on top to collect sunlight, and they have CO2 to collect. They have the photobioreactor to collect CO2, etc. I would say that this is more close to, let's say, sustainability, but not economically efficient systems. Yeah, I would say, well, for us, let's focus on biofuels and not on the other on the other part.
Thank you very much, Janis.
Yeah, thank you.
We have to present the next speaker.
Yes, thanks. Thank you. So the next speaker, I believe she's online, is Sofia Hidalgo Ruiz from CSIC. He's a PhD student, right? Yeah. She's not here. Maybe you can continue.
We continue with the next speaker, Nicolas. The next speaker is Nicolas Spagazzini from VTT. The floor is yours.
Okay, thank you very much, and thanks to join us. So we'd like to talk today about the online source of validation for microalgae bioprocess monitoring. In case we use time-gate Raman spectroscopy and automated microscopy at Python scale. This was a work related with PTT in collaboration with CERS. So that just basically go to the problem here, that with the time we have a lab report biomass, the moment it's gone. So basically what we provide here is a time-gate Raman and automated microscopy to make biomass visible in real time at pilot scale, and we are precise about what that means. So for process control need real-time biomass, microalgae make that hard. FUELGAE turns industrial carbon dioxide into advanced liquid fuel via microalgae. So we have offline labs analysis lags our today, so it's too slow and steer the process. And also we have other issues related to microalgae, autofluorescent swamps, conventional Raman. I don't know if people here is familiar with spectroscopy, but in that case, it's a big issue if you are using conventional Raman. So here, the need is basically continuous in situ multi-parameter sensing for digital twin. That basically be with the future, combined with AI. So what validation means here is that basically online prediction of total biomass, we benchmark against to offline dry cell weight reference at the pilot scale, feed the purpose performance for not, I would say, not for analytical method validation, it's just biomass only at the not component composition. This will be in the future, as a long story short. So this is basically an integrated multi-sensor PHP platform where it was, we just measure performance cell vulgaris cultivation monitoring at CERS in Thessaloniki, Greece. It was 17 pilot campaign. We just deploy 3 sensor systems simultaneously. One time get immersion probe in situ direct contact, and the second one probe was source, or we call a spatially offset Raman spectroscopy probe that is non-invasive, and then we measure through the glass. That's a real thing, though. Also, we provide online microscope that may, in that case, is automatic cell detection for 20x to 100x augmentation. That's a really good thing, though, also. And overall, this continuous automatic measurements over the full cycle, basically full cultivation cycle, and then we basically, validate this information somehow with reference sample collected by offline calibration using dry waste. Okay. For people who is not familiar with time-gate Raman spectroscopy, the gating principle is that we can separate and to get like in the right side, a fluorescence-suppressed Raman spectrum or fluorescence-free Raman spectrum, because it's affected with biomass and not related with biological stuff. We are measured with Raman spectroscopy. The main thing is that we are using pulse laser Raman, and the case of pulse laser is basically we hit the sample with the laser, we receive the Raman photons, and Raman photons are faster than the fluorescence photons, and we can reach using the strategy of time gate, and we can get the right side spectrum that is fluorescence free, and then we can continue measuring during the process, in the case the monitoring. So this is basically 3 sensors, 1 reactor simultaneously and continuously. We use a probe, immersion probe in situ, inside the main fold in the bottom, insert. We use source probe, it's a spatially observed Raman that has been non-invasive. We measure through the glass, and then we combine this technology with the online microscope that it was based, in that case, was bypass loop, using the measurement, using dual microscopy with different technologies also. So the main thing is here, for the workflow step, for the integration pilot is very simple. So basically, we just measure those. We put sensing these 3 sensors in a 70-liter tubular airlift PVR, monitor chlorella vulgaris, 17 days, a campaign growth, extraction, and regrowth. And we combine these 2 sensing systems, 3 systems, and then the photobioreactor to get real-time spectra and images in order to provide a biomass calibration and cell analytics. That will be like information to the overall digital twin information. That will be basically in the next step. It's beyond the scope of this presentation. So basically what validation means here is that because we are focusing the online time-gate Raman spectroscopy, the idea was to biomass prediction every few minutes, and then the idea was to benchmark this with the offline reference. We're using Dray cells, gravimetric, and in the pilot, and then we get for this fit this for purpose agreement with the offline reference at pilot scale. We got a very good resolution correlation with the immersion and the non-invasive probe, that source probe. You can see for the basically to compare with the offline PLS model, that if somebody is familiar with the chemometric thing. So we claim this is a total biomass online and pilot scale. So here just, I go a little bit fast. Here we just prepare this. We can see time gate to recovering clean, time resolve Raman spectra. At fluorescent culture, we can observe both spectra, data sets that for immersion and source probe. After pre-processing, there's almost not pre-processing at all. It's just basically to get all the features related with the Raman spectrum. And we can track all the growth related, and then we can track also all the important bands related with the process, protein, lipids, and carotenoids. So, yeah. Also, we can basically go to results, some simple results to become Raman tracks biomass growth and temporal dynamics. In the case, you can basically say that's a very simple PCA. We can extract all the information related and all the variation related with the lipids and carotenoids. And in the loadings, that you can basically see all the dynamics, and also we can also track all the information in the scores that related with the time dynamics. So that was really a good thing, that in order to combine all the information. Also, we have equivalent information in the source probe, a little bit with dispersion, because we measure with the same device. They have to switch the fiber optics with the different probes, but the information is basically equivalent in the chemical composition. So this is basically online biomass follow the offline reference across the campaign. So we use basically offline PLS model in order to track all the monitor, all the spectrum across the process, and basically we provide information, all the predicted biomass for immersion probe and the source probe, and then it was really good prediction, I would say. And then we can get that good correlation for both cases. Of course, we have some dispersion because it's our first time ever we measure through glass. That's a good thing, though. And the good thing is that we are able to know in the future, maybe in the next couple of years, to use an equivalent technology the way you don't need even use immersion probe. We can use in a probe that is we can measure through the glass. Immersion probes at least is 5.7 higher SNR compared with the non-invasive recover, but it's equivalent in chemical information through the glass. That's a real thing here. So in the other hand, so we combine this information with the online microscope at an independent, in the case of cell level information and confirmation that, so we can see here in the right side, the cell detection basically versus time. So we can basically see all the detections. So for 20 and 100x objective running continuously over more than 60 hours, 360 hours, with detection, we was about 20x for around 3,000 cells, around 50 cells per hour, and for 100x, around 300 cells, and it was around 10 cells per hour. Availability was up to 92% for 20x. We exceed KPIs for most of the run, and also we add the morphology that bulk spectroscopy cannot see. So that's a really important and complementary information related with the spectroscopy. Okay. So as a validated PAT suite feeding the FUELGAE digital twin. So here the idea was to multi-sensor and PAT validate at pilot scale. The idea was to move from TLT4 to 4.5. We provide real-time spectral imaging feed, the digital twin and predictive monitoring and closed-loop control, and direct support for the value chain for microalgae biomass and renewable fuels. Okay, I would like to, thanks to my colleagues in Technical Research Center of Finland and Optical Sensing System team, Akimaira, Jarkko, and Leinen, and also people from CERT, that we made a very good measurement and experiments with Alexandros Pavlon and Janis Penglo. And this work was, of course, funded by European Union, Horizon Europe. And the takeaway for this is basically this presentation is continuous validated biomass at pilot scale, total biomass online, no composition, no overclaim. 2 probes plus 1 microscope probe. We have good correlation, and we are working now already to go until to 4.5. Okay, thank you very much, and welcome for questions. Yeah.
Thank you very much, Nicolas, for your kind presentation. Any questions? We have time for a question. I have a question for you. Is possible to use this type of sensor in other technologies, for example, in the fragmentation of the microalgae?
Yeah, I think that the good thing is that the fragmentation is the process is provided, if the fragmentation occur, and this is in solution, we can measure those with sensing with those things. I would say yes, absolutely, and also we can try to also to use this technology for with high temperature and different things like it's not able to do that right now, but yeah, we can provide this information. Yeah.
Thank you very much.
Thank you very much.
Any other question? It's okay.
Yeah, thank you, Nicolas. So let's give one more try to online speakers. So Sofia Hildago from Ruiz from CSIC. If she's online, she will present us about the development of the microalgae treatment using hydrated inorganic salts. Yeah, Sofia, can you hear us? Are you online?
Hello.
Yeah,
Can you
hi.
hear me?
Yeah, the floor is yours. Yeah.
Thank you. Thank you for your previous presentation, Yanis. Hello, everyone. I'm Sofia Hidalgo Ruiz. Today, I am going to present the work I carry out within the European project FUELGAE as a part of my PhD thesis, specifically development of microalgae treatment using hydrated inorganic salts for the production of advanced liquid fuels. One of the main environmental problems today is the emission of greenhouse gases. Most CO2 emissions come from human activities, especially the combustion of fossil fuels. Some of the main sources are industrial processes, industrial agriculture, oil production, or transport. The aim of FUELGAE is to convert CO2 into advanced liquid fuels, ALF. The project captures CO2 from intensive industry and biorefinery and uses it to cultivate microalgae adapted to each CO2 source. During the growth, the microalgae produce some compounds, such as lipids or carbohydrates, and we can transform this compound into ALF for maritime and air transport. The project aims to develop different technologies to carry out the production of advanced liquid fuels. First, selective production of microalgae. Second, alternative treatment, innovative catalytic enhancement systems from lipids and biocrude, and digital twins and online sensors. In my presentation, I will focus on alternative treatments. The typical extraction technique can be chemical, physical, or biological, or the combination of them. These techniques require large amounts of energy or chemical, making them inefficient. FUELGAE proposed several alternative treatments, and now I am going to focus in the inorganic salt hydrated and solvent. The solvents are cheap, recyclable, not toxic, and require low temperatures. In the treatment proposed by FUELGAE, the microalgae drying process is eliminated or reduced, making them efficient. The inorganic salt hydrated are ionic compounds that include water molecules integrated into their crystalline structure. They are liquid at room temperature. We can see in this picture. We use the ISH to derive the microalgal cell wall, and we select 3 hydrated inorganic salts backed by scientific literature. This is the procedure for the method of treating microalgae with the salt, the hydrated salt. First, we need mix the salt with the microalgae, with the biomass, in the reactor at determined temperature, determined time. Next, we add the solvent, in this case hexane, and wait 2 to 4 hours. Next, we need centrifugate the mixture, and we obtain 2 phases, organic phase and aqueous phase. In this case, the aqueous phase has the salt and waste. We need the organic phase, and we need evaporate the solvent. And finally, we obtain only the lipids. We analyze the extracted lipid with following the official RED protocol. This is a direct method for calculating total triglyceride. The method is called determination of total lipids of fatty acid methyl esters by in situ transesterification. This is the procedure of the transesterification of total lipids. First, we measure the lipids, and we add the solvent and the acid, and we put the mixture at 85 degrees Celsius for 1 hour. We add the hexane, the solvent, in this case is hexane, and let it rest for 1 to 4 hours. In this case, we need the upper phase, and we can analyze by gas chromatography. In this slide, we can observe the result at 70 degrees Celsius. We observe the better result is with the iron salt. In this slide, we can observe the result at 110 degrees Celsius. And now we can observe the better result with iron salt. And now we obtain more lipids with zinc salt. And we can say that the neutral pH of the hydrated lithium salt limited lipid recovery capacity. In contrast, the hydrated zinc salt and iron salt, due to their acidic nature, achieve higher percentage of lipid recovery. And in this slide, we can observe the result with the iron salt at different temperature. And we can say the extraction increases with increasing the temperature. So the main conclusion are the neutral pH of the hydrated lithium salt, limited lipid recovery capacity. In contrast, the hydrated zinc salt and iron salt, due to their acidic nature, achieve a higher percentage of lipid recovery. The highest lipid extraction yield is obtained using the hydrated iron salt at 110 degrees Celsius. And finally, the extraction increases with increasing temperature. I would like to thank the European Union for funding this project. And in this picture, we can observe my research group. Thank you.
Thank you very much, Sofia, for keeping the time as well. Many questions we have for Sofia? Yes, please.
Hello, Sofia.
Hello.
The microalgae is dry or wet?
We are working with dry microalgae. Yes, but we use in some time with we working with wet microalgae, and the result is better. Yes.
Thank you.
Thank you. Any other questions? Maybe we can have one more short question or not? Yeah. If not, let's move. I believe we have another online speaker, Evie Beku from Analysis DSC. She will speak about CFD-derived digital twin for predictive operation of photobioreactors. So, Evie, can you hear us?
Yes. Can you hear me?
Yeah, please, yes.
Okay. Hello, my name is Evangelia Beku from IDSC. As part of the FUELGAE project, our work focuses on developing a digital twin framework that supports the conversion of CO2 into advanced biofuels. Today, I will present our work on the development of CFD-derived digital twin for photobioreactors developed within the FUELGAE project. The objective of this work is to combine hydrodynamics, gas-liquid mass transfer, and algal growth modeling into a predictive framework capable of supporting photobioreactor operation and process analysis. CFD simulation is computationally prohibitive for operational use. In this work, we develop a CFD-derived digital twin framework that combines informed surrogate models with algal growth kinetics, enabling rapid prediction of photobioreactor performance under varying operation conditions. Before discussing the digital twin itself, it's important to understand the fundamental challenge in photobioreactor operation. Photobioreactor productivity is an emergent property arising from the coupling of hydrodynamics, gas-liquid mass transfer, radiative transfer, and biological growth kinetics. A traditional growth model typically assume homogeneous conditions and therefore cannot adequately represent the spatial differences that develop within industrial scale system. CFD provides access to these local transport processes and enables qualification of the mechanisms that ultimately control carbon utilization and biomass productivity. Having established while CFD provides detailed insight into reactor behavior, it is computationally too expensive for operation decision making. A single simulation may require several days of computation, making real-time application impractical. Our approach is to use CFD as a knowledge generation tool. We first perform CFD simulation across the operating space of interest and extract the key hydrodynamic and mass transfer descriptors, including gas holdup, interfacial area, and mass transfer coefficients. These CFD-derived responses are then used to contrast response surface models, creating computationally efficient surrogate models that retain the underlying physical relationship identified by the CFD simulations. The surrogate models are afterwards embedded within the digital twin, enabling rapid prediction of reactor behavior under varying operation conditions. As a result, prediction that will normally require approximately 1 week of CFD computation can be obtained in less than a second with the digital twin environment. This represents a computational speed up of several orders of magnitude while preserving the essential process physics required for predictive operation, scenario analysis, and optimization. In other words, the digital twin combines the fidelity of CFD-informed knowledge with the speed required for real-time decision support. To generate the surrogate model, we first developed a high-fidelity CFD representation of the tubular photobioreactor. The model represents a 6-tube reactor with a working volume of approximately 70 liters and includes the key physical phenomena covering reactor performance. Hydrodynamics were simulated using an Euler-Euler multi-phase framework, while gas-liquid mass transfer was represented through CO2 dissolution and a multi-size group bubble population model to compute bubble size effects. The objective of the CFD simulations are not simply to visualize flow patterns, but to quantify the transport parameters that directly influence biological performance. In particular, we extracted key descriptors, including gas holdup, gas-liquid interfacial area, and volumetric mass transfer coefficients. The simulations were performed across inlet CO2 concentration ranging from 5 to 30% by volume, which corresponds to the operating rates considered in this study. The velocity field shown on the right indicates a relative uniform flow distribution across the reactor tubes. These CFD-derived transport descriptors are then used to construct the surrogate models embedded within the digital twin. Once the CFD model was established, we investigated how increasing the inlet CO2 concentration affects hydrodynamics, mass transfer, and carbon availability within the reactor. The figure on the left shows representative CFD predictions of the dissolved CO2 distribution inside the tubular photobioreactor. As expected, increasing the inlet CO2 concentration substantially increases the amount of dissolved CO2 available within the cultivation system. To quantify this behavior, we extracted the key transport descriptors used later in the digital twin and normalized their responses as shown on the right. The most important observation is that dissolved CO2 increases dramatically across the investigated operating range, with an increase of approximately 6-fold between 5 and 30% CO2. The hydrodynamic transport descriptors, including gas holdup, interfacial area, and mass transfer coefficient, change only marginally, with variations below approximately 6%. This indicates that increasing the inlet CO2 concentration initially affects carbon availability rather than reactor hydrodynamics. More importantly, the results reveal diminishing return behavior. Beyond approximately 10 to 15% CO2, additional increases provide only limited improvement in the transport-related quantities. This suggests that the process is progressively shifting away from a mass transfer control regime and towards biological or light-related limitations. From an operational perspective, this is an important finding because it indicates that simply increasing CO2 supply may not translate into proportional productivity gains. They may instead lead to insufficient carbon utilization. The next step was to transfer the CFD-generated knowledge into a form that can be evaluated in real time within the digital twin. The surrogate acts as a reduced order representation of the CFD solution space. Instead of repeatedly solving the governing transport equations, the digital twin queries a response surface contracted from CFD-generated operating data, providing instantaneous access to hydrodynamic and mass transfer predictions within the validated design space. These slides demonstrate the integration of CFD-derived surrogate model into the photobioreactor digital twin. Rather than operating as a standalone model, the surrogate is now embedded directly within the digital twin environment and can be accessed through the standard user interface. The user specifies the operating condition, in this case, the inlet CO2 concentration, and the digital twin immediately predicts the key transport descriptors obtained from CFD analysis. This include gas liquid interfacial area, gas holdup, dissolved CO2 concentration, and the mass transfer coefficient. The embedded visualization tools also allow users to review the response surfaces and examine how these transport parameters vary across the operating range. All predictions are generated in real time, enabling rapid scenario evaluation without the need to execute additional CFD simulations. This demonstrates the practical implementation of the CFD-derived digital twin concept, where high-fidelity CFD knowledge is made available directly to end users through an operational decision support platform. What is interesting here is that dissolved CO2 responds very strongly to increasing inlet CO2 concentration, while the hydrodynamic descriptors remain relatively stable. This further supports the conclusion that increasing CO2 preliminarily changes carbon availability rather than reactor hydrodynamics. This slide represents the final integration step of the framework, where the CFD-informed transport predictors are coupled with the biological growth models within the digital twin. Up to this point, we have shown how CFD simulations were used to characterize hydrodynamics and mass transfer, how surrogate models were developed, and how those surrogates were embedded into the digital twin. The final objective is to translate this transport prediction into biomass growth predictions. In the current implementation, the CFD-derived transport descriptors are available in real time within the digital twin and can be used as inputs to multiple algal growth models. This allows users to evaluate different growth kinetics formulations under varying operating conditions and assess how changes in CO2 availability influences biomass production. The figure illustrates examples of growth predictions generated using different model formulations, highlighting the capability to compare alternative biological assumptions within a common framework. In this way, the digital twin links reactor scale transport phenomena directly to cultivation performance, providing a more mechanistic basis for productivity prediction than conventional standalone growth models. Looking forward, the framework has been designed to support additional capabilities, including image-based biomass estimation, sensor-driven model calibration, and ultimately real-time optimization and predictive operations of photobioreactors. Overall, the work demonstrates how CFD-derived process knowledge can be transformed into an operational digital twin capable of supporting real-time prediction and future intelligent photobioreactor operation. Thank you for your attention, and I'll be happy to answer any questions.
Thank you very much, Evi. Also for keeping the time. 1 or 2 minutes for questions. We have any from the audience? Yeah, maybe I can start. So Evi, well, you work on models and you need data. Beyond, let's say, the typical monitoring of like optical density or biomass or this type of parameters, which are the most important things to measure if we would like to focus on more advanced systems? So, for example, any bubble sizes, any of that, so which is more important? And the second part will be for us working on the photobioreactors, what parameters to focus on for the optimization?
Yes, that's a very good question, Yanni. We would like to extend the work on the light intensity, like to see how light interferes with biomass growth, because as you know, when biomass is grown, it inhibits the light intensity. So any measures regarding that, or the pH, or the temperature, how it changes, and how the photobioreactor is cooled down, and also how oxygen and CO2 escape the photobioreactor to begin with. There are a lot of things, actually. I can go on, but yeah.
Okay, thank you, Evi.
Thank you.
Maybe a short question or not? Well, actually, we're well in time now, so maybe we can move.
Okay. Last speaker is Andrea Rodenas from ITN Spain, and Carla Bartolome. We have a presentation about the environmental life cycle assessment and advanced biofuel production from microalgae. The floor is yours, Carla.
Thank you, Silvia. So, well, I'm Carla Bartolome from ITN. We are a research center located in Valencia, Spain, and together with my colleague Andrea, we will present the life cycle assessment of the FUELGAE project. Okay, so, well, our objective is to evaluate the environmental impacts of the integrated biorefineries of the processes of FUELGAE. But also, when we want to compare with the conventional fuels, we have to add also the distribution and transport emissions and also the combustion emissions. So we analyze a whole well-to-wake, we did a whole well-to-wake assessment. The functional unit of our life cycle assessment is the production of 1 megajoule of biofuel as part of the integrated biorefinery yearly output. And we did energy allocation, and we used the methodology CML baseline and also the ICC for splitting between global warming potential fossil and biogenic. So here you have the flow of case one. We have 2 different case studies. The main difference of these 2 case studies, apart from the microalgae stain, is the origin of the CO2 that is fed into this photobioreactor. So in case one, this CO2 comes from a biogenic source. So we have this bioethanol plant, and this CO2 is fed to the photobioreactor. And then with the fractioning, we have like 2 different chains. We have this residual biomass that undergoes the hydrothermal liquefaction, and then we have the hydrotreatment and the bio-oil, and then with the polysaccharides that are fed to the bioethanol plant, and we have this 3G bioethanol. And we did energy allocation, which means all the percentages that you see here. So all the impacts are allocated, well, in the chain of the residual biomass to the bio-oil, and in the chain of the bioethanol plant to the bioethanol. And for case 2, which is the steel plant, here the CO2 that it's fed to the microalgae, it comes from a fossil source, and the steel plant is outside the limits of the system. And it's very similar. We have this photobioreactor, and then the fractioning of the microalgae, and then we have these 2 chains of lipids and residual biomass. And for the residual biomass, it goes to anaerobic digestion, and all of the impacts of this chain are allocated to the biomethane. And in the case of the lipids, all of the impacts are allocated to the bio-oil. So we did an attributional LCA, which means we focus exclusively on the impacts that are within the system boundaries. So which is also supported by sectorial guides, as you have it here at Corsia, and no avoided emissions outside the system are considered. which is very important, is to differentiate between the two case studies, because in case one, we have this source for the microalgae that it comes from a biogenic source. So this CO2 that is captured, it does not disappear. It's also emitted in the combustion, but in the global warming potential biogenic, which is different for case two. Well, the biofuel, well, the microalgae capture the CO2, and then the CO2 is emitted in the combustion stage. And we also applied, as in other LCA studies that we have seen of biofuels, we did also, we also included the credits for the fossil CO2 captured by microalgae in the case two study. So now we show some of the results here in this presentation. So these are the results for the case one bioethanol plant. Here you can see that all of the environmental impact categories that we analyzed, and also the different stages of case one, the bioethanol plant. So, which is really interesting, were the hotspots of this assessment. So in the photoreactor, we found that the nutrients and also the energy consumption, but mostly the nutrients, are one of the most impactful inputs that we have. Also in the hydrotreatment, the effluent that is generated, so this waste stream, and in the hydrothermal liquefaction, the thermal energy of the process. This means that for next steps, we are working on the nutrients part, so we could see if we can do some sort of nutrient recovery, and also in the energy optimization. And also, yes, we added some energy credits from the hydrotreatment. We got a gas stream that could produce energy for this biorefinery, and it allows to reduce up to 9% in some of the impact categories. And now we would like to show you also the net results for the global warming potential fossil. Okay, so in this slide, you can see a graphic when we have the results per gram of CO2 equivalent per megajoule, so like the functional unit. And in green, which is the well-to-tank, is the production stage. In orange, which is the tank-to-wake, is the combustion stage. We also have CO2 that is sequestered by biochar in purple, and then in well-to-wake is the net result. It's a dark green circle. So what the main difference that you can see between the bio-oil that we obtain in FUELGAE and the conventional fuel is where the main impact on this global warming potential fossil it's being produced. So for instance, in the fossil kerosene, you can see that it's on the combustion stage, whereas in bio-oil for aviation, it's in the combustion stage. Okay, this does not mean that it doesn't have any impact on the combustion stage, but we are focusing on fossil global warming potential. So if we want to see the combustion impact, it should be on a graphic dedicated specifically to the global warming potential biogenic. But due to time constraint, we only included the fossil. Well, the results are that more or less our results are 50 grams of CO2 per megajoule in the bio-oil for aviation and for maritime sector. There is a slight difference in the combustion. And if you can see, well, it's 43% reduced. Well, it's reduced the impact when compared to fossil kerosene. And when we compare to conventional marine fuel oil, then it's 47%. And now I leave the floor to my colleague Andrea.
Thank you, Carla. Let's move to the case study 2 with fossil CO2 capture for a steel plant. So in this case, the main hotspots are the lipid extractions due to the energy for thermal requirements, and in the photobioreactor caused by nutrients and energy consumption. Also, the effluent gas for the hydrotreatment have energy, so we add credits from this energy that in this case is more significant than in case one. This credit represents approximately a reduction of 27% in global warming impact category. So the results from the carbon footprints in the aviation sector in well-to-wake scope are 107 grams of CO2 equivalents per megajoule. And if we include the credits for CO2 capture, the fossil CO2, this is system expansion approach, we obtain a reduction of 38% compared to fossil kerosene. And similar in maritime sector, with the reduction that we achieve is 43% compared with conventional marine fuel oil. In the graph, we can see in blue the fossil CO2 capture, but then is emitted in the combustion. So, as conclusion of the FUELGAE project, the results that we obtain highlight the potential of microalgae as a sustainable alternative feedstock for the production of biofuels. In case one, we obtained a reduction of impacts of 43% and 47% compared to aviation and maritime sector. And in case two, when we applied system expansion, including the CO2 fossil capture, the reduction is about 38% and 45% compared with these sectors. So in the project, we still have more than 1 year to continue working in the optimization of the nutrient supply and improving the energy efficiency. So in the main process that are key elements for achieve competitive performance in this hard-to-abate sector, that is in aviation and maritime transport. So this is our contact, so thank you for your attention.
Thank you very much for both for your interesting presentation. We have time for 2 questions. There are any questions online people or present, please?
Oh, thank you for the nice presentation. Only a question. I haven't seen regarding the impact categories related to the harvesting from the biomass. How you take down this kind of action?
Can you repeat the question?
The growth of the biomass?
No, the harvesting, the recovery of the biomass. How is the type that you used? Because only we apply this kind of study, and we used some tools for our harvesting, like membrane inside the photobioreactor, and this will a very high impact. In our case, how is done the harvesting from the biomass?
Yeah. I think the harvesting, well, is in the photobioreactor. So one of the main hotspots of the analysis is the nutrients that are fed. So more or less it's because of this. So we have we model the photobioreactor with all the inputs that are needed for the microalgae to grow. And the main hotspot is the photobioreactor, in the photobioreactor, the nutrients. And it is, I don't know if we can go some slides, or it's just, the presentation to show them where it could be. Okay. Then mostly is the nutrients, and in categories such as acidification, eutrophication, and so on.
Maybe I can help a little bit here. So, well, us working on the photobioreactors, then CSIC working on the downstream processing. In between, of course, you have to harvest, and maybe you need to dry. We have different concepts, and so the first thing that you definitely need to do is to at least not completely harvest, but at least concentrate biomass. So this happens by filtration, standard filtration. So to concentrate biomass, let's say 10 times, that's it. But from that step to fractionation and recovery lipids, polysaccharides, etc., this is conceptual because CSIC is developing technologies that can be used for wet biomass or for dry biomass or whatever. So all of that will be reflected in different scenarios, but I guess we decided here just only to showcase one scenario. But what we know, we don't focus actually on the research on the harvesting. So the membrane filtration is just a standard system. That's it, with all the impact it has, of course. Yeah, of course. Yeah.
Thank you.
Yeah.
Hi, thank you. Thank you for the presentation. Just a quick question. Have you, in regards to the bioethanol plant, I presume this includes enzymatic hydrolysis and fermentation and distillation probably for delivering, let's say, the output. Are you also including this in your analysis when it comes to the environmental impacts?
Yes, so I mean, we included all the information that we have for the bioethanol plant, but most of this information, well, it's a model, well, by Marco that will be presented later. But yes, we included all the inputs that we have, and we also treat it as like a black box. So on the bioethanol plant, so it's mostly like we don't have it differentiated by different stages. Just like a black box, and all the inputs and outputs.
I understand, because to our knowledge, because we have similar, let's say, approaches, there is some sort of an impact when it comes to the operation. Also using enzymes adds on to the environmental impact. Thank you. Thank you very much.
Okay, now we move to Marco Ochenogia from University of Oulu. He will discuss on the optimization of microalgae-derived biofuel systems with using a shortcut modeling approach. So, Marco.
Yes, so thank you. Yeah, I will be introducing one part of the FUELGAE, or some activities on the FUELGAE project related to the process modeling and providing also the mass and energy balances for the LCA analysis, and on the same time creating also tools for the digital twin, what was also discussed in the previous presentations. So this work was done by me and my colleagues Christian, Jani, and Mika. Before moving to the subject, I also want to a little bit highlight where I come. So maybe I'm the most northernmost participant in this conference, coming from Oulu, Finland, and our university has 8 faculties, around 15,000 students, and 4,300 staff members. I represent Faculty of Technology and their control engineering research group, and we focus our research on mathematical modeling, process control, sensor fusion, data analytics, and optimization. And what is also related to this study, what I'm presenting now, is the model reliability assessment in model-based control systems, or predictive simulation-aided optimization with uncertainties. As a background on motivation for our part in the FUELGAE project and this presentation is that we do need a holistic approach and view of the integrated processing plants, and there also the advanced control enabling technologies, real-time monitoring, digital twin plays an important role. However, in bio-based processes, there are inherent limitations for use of such things. For example, small plant scales, product diversity, unavailability of high fidelity process models, for example, and this limits the use of typical process system engineering tools for the optimization and scale up. On the other hand, let's say simple reconfigurable process models can be used to study process interactions, disturbances, uncertainties. So everything what is needed to really study the impacts of each of the individual processing units to the integrated process plant and to perform the plant-wide process optimization. So I will be shortly presenting the first steps taken during the FUELGAE project towards holistic plant-wide optimization by little bit highlighting what the modeling literature revealed during the project, and then I will continue with the steady-state plant-wide model, what was or is suitable for process design analysis, and bringing those mass balance, energy balance calculations for the subsequent analysis. And we decided that we want to focus on this kind of shortcut models or surrogate models, which we can also update if we are ending up with different assumptions of the processing technologies, microalgae species, and so on. So we can update the model quite flexibly when the project is advancing and new results arrive. As mentioned in the previous presentation, the project has 2 case studies. In this presentation, we will be focusing on case study number 2, where also in this interpretation there is also the dewatering step related to the harvesting also included, followed by lipid extraction, and that lipid fatty acid stream then goes to hydrotreatment and the subsequent distillation to produce the advanced liquid biofuels. And also we incorporated in our model the hydrogen recovery for that step, because hydrotreatment requires presence of excess hydrogen, and we had to assume some technology to recover that excess hydrogen back to the process. Then the residual biomass can be fed to the anaerobic digestion, where we can produce biogas or biomethane as an energy carrier. This model version is implemented in Excel spreadsheets, so we do have some inputs what the user can change, and then focusing on the output side for some specific key performance indicators for the integrated processing plant, meaning water consumptions, energy consumptions, and productions in total. So going through the model components shortly, photobioreactors were already discussed, and also in this case we are focusing on airlift tubular PBR configurations, and there are lots of earlier studies related on this, and during the project we are adapting more detailed model for these purposes as well. But at the moment we took a simple surrogate model to represent the biomass growth in these preliminary mass balances. Then for the lipid extraction, there exist different kind of methods, and one of those is highlighted in this case study, and we needed to develop also Aspen simulation model for this to evaluate the performance of the processing system, and also it was highlighted that of course the water content of the biomass entering this type of extraction is an important variable affecting the economics. So there is also some literature related on that. Thirdly, the hydrotreatment step, including the hydrogen recovery and distillation, was embedded to condition the bio oil using elevated pressure and temperature and catalysts. And as mentioned, the excess hydrogen needs to be used, and also needs to be recycled in the integrated process. Currently, we are only using fixed yield values yield values for this step, but for the energy calculations, so we do have models for the complete process comprising conditional and reactive source and separation stages, as well as the heat integration between the feed and product streams. Regarding the hydrogen recovery technology, we assumed vacuum swing adsorption, and also for that part, we utilized the data from literature to identify simple linear quadratic model to allow some flexibility to that step to later optimization studies, where we can play a little bit with the process conditions and see how the overall efficiency of the integrated plant is affected by the operation conditions. Finally, for the AD, the way to go was to select the state-of-the-art ADM1 model, and for the steady-state calculations, we chose the R4 version of it, which has reduced dimensionality, so it's quite easy to solve from that version, the steady-state solution for the Excel implementation. Again, this model can be refitted when new project data arrives to really better describe the kinetics related to the microalgae biomass. Okay, then some example of the results, what we have done with the model so far. So we do have the baseline scenario, and then we created an alternative process scenario which focuses a little bit on the valorization of one of the streams, namely the nitrogen and water recovery potential from the AD digested. I'm not an expert on AD process, but according to literature, there are of course several technologies for that recovery, and like 65 to 80% could be of the nitrogen nutrients could be recyclable from the biomass in back to the photobioreactor if we are using some simple pretreatments for the digested, and even better recoveries can be achieved even when ammonia stripping and absorption are employed. But yeah, we took the first approach as a first test to see that what kind of impacts we have for the overall process KPIs with this recycle step. Regarding the biomass production, bio-oil production, there is of course no changes because we are only looking at some changes for the downstream processing, and due to the fact that we can close some of the water loops, so there is significant difference in the water consumed and also the amount of wastewater produced in this integrated process plant. We are not considering here the potential energy penalties associated with the pretreatment of the and recycling of that digestate. So there, in the results, there is no changes with the energy consumption either. But that is something what needs to be looked more carefully in future simulations. In total, 73% of the nitrogen carried by the biomass can be recycled with the digestate preprocessing and direct utilization in a photobioreactor, and this has economic and environmental impacts as the nutrient recycling reduces the demand of energy-intensive synthetic fertilizers and also mitigates the nitrogen losses to the environment with the wastewater or the digestate. Another set of simulations we did was to study the uncertainty of some of the assumptions. So we made a set of simulations with the different parameter values to see that what kind of impact we create by selecting, or making some simplification and selecting some parameter values. So on right, you can see kind of box plots with a set of simulations and what kind of deviations were found. So we tracked back that what was the cause of the deviation in each case and highlighted some of these uncertainties which should be taken into account in the LCA or TEA analysis. So my time is seems to be taken, but you can find the conclusions from this slide. What I want to emphasize is that the future work will also extend the model to represent the dynamic process behavior in different environment, and this will enable optimization of plant operation under changing environment and conditions such as variations in biomass growth, light intensity, and, for example, energy prices. Yes, thank you.
Thank you, Marco. We can have one short question. Yeah. Well, maybe I can ask one. From the different components of the models, can you select one being the least reliable and the one that you need to focus more in the future?
Yeah, that's interesting. Of course, yeah, the photobioreactor model maybe is something where you can spend years of studies, and you would be needing lots of experimental data to back up your assumptions. But what I need to focus in this current model versions would be updating any information for the hydrotreatment part, which is where the experimental part of the project is still ongoing. So that is the main focus, to improve the model.
Okay. Thank you. We can proceed with the presentation coming from Ylva Katarina Wetmark from Northern Norway. She will present us algae salt project, which is about a sustainable aviation and shipping fuels from microalgae and direct solar technologies. So thank you, welcome, and the floor is yours.
Thank you for that warm introduction. Sustainable aviation and shipping fuels from microalgae and direct solar best technologies, and it's what we work with in AlgaeSol. First, a little introduction about Norse Research, where I work. We are a Norwegian research institute based mostly in Bergen, but we have locations all over Norway. And we focus on applied research and have a lot of collaboration across both private and public sectors. And our research topics are very broad, and we focus on renewable energy systems, climate research, health and society, and my faculty specifically work on biotechnology and circular economy. In AlgaeSol, we are the coordinating institute, and we also have two tasks, which is the sustainability assessment assigned to me, and my colleagues doing microalgae strain development, and I will go more into detail on that. First, a little introduction to sort of the problem we're trying to solve. Both the shipping and aviation industry are heavy emitters of greenhouse gases, and the sector has been struggling for many years to transition to renewable fuels. So even though it's a very pressing issue, it's coming more and more important to decarbonize this sector. though it faces a lot of challenges. In this graph here, we can see a figure from a net zero roadmap from the IEA that predicts how we can transition both sectors. And as you can see, toward 50-50, we will have a significant increase in biofuels and other renewable fuels. But in both the shipping and aviation industry, biofuels will become a significant part of the solution here. However, there are a few key challenges facing the biofuel sector, namely the limited feedstock availability. To produce fuels from biomass, you need a lot of biomass, much more than you need for fossils. So getting all the biomass is going to be challenging. In addition, compared to fossils and chemical industry, bio-based systems have a lower energy conversion efficiency because they rely on complex metabolic pathways, which might convert energy a little bit less efficient. So in Algisol, we wanted to address all these challenges and develop value chains that can use sunlight, CO2, and wastewater residues to convert them into sustainable biofuels. And by that, accelerate the replacement of fossil-based fuels. So this is a short overview of the whole project. We are developing 3 separate value chains, all based on these BES systems, or bioelectrochemical systems, which are the batteries you see at the left side. And then these produce the respective biofuels for shipping and aviation. We also, in the project, develop the necessary processes to convert the incoming flows. So, for example, the methane and methanol, and purify them using membrane-based technologies. And for the third value chain, is even more complex. There we combine these bioelectrochemical systems with microalgae, integrates that so that the effluent from the BES system is used to feed microalgae. And then we isolate the lipids and the rest of the biomass, and it's processed in each process separately. So we have hydrotreatment to make sustainable aircraft fuel from the oil, and the rest of the biomass is treated by anaerobic digestion combined with a BES system to produce biogas, which we then use the methane for shipping. In addition, to effectivize these systems, we're also implementing a task that improves the lipid productivity of the microalgae by inducing mutation so that they genetically grow faster. And we also implement custom contamination control to prevent culture crashers. Along with that, we also develop process simulations and do perform sustainability analysis to ensure that these systems are sustainable and realistic. Now I'll go deeper into the technologies. So in the top figures there, you can see how these bioelectrochemical systems work. There are 2 components, the anode and the cathode. So the anode is coated with a photoactive material so that they can use sunlight and excite electrons and generate a current. That current feeds into the cathode side, which is populated by microbes. And so these electrons can function as electron donors to their metabolic pathways, thereby stimulating them to produce biogas. In this third value chain that I showed you, it's even more complicated because we are integrating the photoanode, a biocathode, that this time produces acetate from CO2 instead of biogas. And then that acetate is used to feed into the microalgae cultivation system. And this cultivation system grows Chlorella sorokiniana. And this species is capable of mixotrophic growth, which means that it can photosynthesize by day, and during the night it can heterotrophically feed on this acetate. So in theory, this could be a continuous cultivation. And then we have the downstream processes. So we use membrane separation-based techniques, both for the liquid stream and the gas stream. These membranes are customized and fabricated so that they can work specifically on the different flows. We are trying to optimize different parameters to account for sustainability, trying to save energy in the production process, and so on. The membrane-based technology is also used to up-concentrate the microalgae biomass to about 10 times. And then for the rest, we have to up-concentrate it further with centrifuge. Then you have the downstream lipid processing, where we are researching on using extraction via ultrasound and NADIs, or what is called natural deep eutectic solvents. The reason we chose natural solvents as opposed to inorganic solvents is to see if we can improve sustainability using these different NADIs. And finally, we also have a task on fuel upgrading, or purifying the lipid. And that is also achieved by hydrotreating. And the project looks at different catalysts and see if they can find both a cost-effective, sustainable, and just technically effective system that can treat the lipid biomass and convert it to sustainable fuel. Yes, and some highlights, what we have achieved so far in the project. We have, in the photoanode development, developed 3 different photoanodes that all achieve high efficiency comparable to state-of-art. When they also they initially used water for the oxidation reaction, but when they then switched to organic solvents, they were able to improve the efficiency 50% more. So that's good news. And for the biocathodes, we achieved a stable methane production, achieving a theoretic efficiency of 70%, which means that the theoretical production limit, we hit 70% of that limit. And then we also modified microalgae strains using random mutagenesis methods, which sort of stimulate natural mutations. And we found that these had increased in productivity, varying from 50 to 100%. Finally, on the figure to the right here, I have a picture of the integrated BESS microalgae system. So you can see the small photobioreactor to the left, and then there's a thin steel plate on the right, which is the BESS system. So these were successfully integrated at lab scale. As I mentioned, we're also doing a life cycle assessment in this work. We have sort of 2 targets with this sustainability analysis. First of all, we saw that there's a lot of experimental alternatives that they're working on in the lab. And for them, it's very useful to know which of these alternatives are the most sustainable and cost-effective. So in this figure, I summarized all the three value chains, and in the green bubbles and in the yellow bubbles, you can see all the different technological alternatives that they're experimenting with in the lab that we're also going to compare from a sustainability perspective. Thereby, we hope to actually use the LCA method to also guide the development directly in the lab. And the next step of the sustainability assessment will be to assess this at large scale and compare it with conventional fuels and see if it is actually sustainable and realistic in a real industrial setting. Yes. So, in summary, we see that Algisol offer a solution to the next generation biofuels. It can reduce feedstock limitations by using both direct sunlight and the wastewater to produce these bio-based fuels, and also by inducing the biological productivity. Though we still face a lot of challenges when trying to optimize and scale up these systems, there are still many questions unresolved when it comes to scale up, and therefore an uncertainty that has to be addressed at some point. And trying to also make it cost effective and sustainable is also going to be a question and an upcoming challenge. And we can see that we use early stage LCA to guide development of these fuel systems. Thank you so much for my talk.
Thank you very much for this interesting presentation of the project and of some of the individual components and the technology. So any question, a quick question we can accommodate? Yeah. Yes, Sophia.
Hello, thank you very much for your presentation. It was very interesting. And this whole high innovative system. Could you elaborate a little bit more which you consider that will be the main challenges for the scale up of the process and the main limitations?
Yeah, so currently the bioelectrochemical systems that we are researching in the lab are at the square centimeter scale. And they have a production limit of maybe a few grams per day, per hour. And when you just scale that up linearly, it's really not enough to make a good production system. So there are some scale limitations to these because they can have a total area maximum of 1 square meter, and to reach the production levels that you would typically see in a biogas plant, you would need maybe 1 million of those. So it's we're talking a lot scale here, and yeah, figuring out how to scale it, we also are not quite sure yet.
Okay, thank you.
A quick question myself as well. Yeah, you said that you're using wastewater.
Yes.
Yeah? And also you're allowing like mixotrophic and aerotrophic conditions. So any contamination issues for that? So covering something from the wastewater, and also maybe it's more challenging for the algae to keep their, let's say, their new capabilities after the mutagenesis. So any issues with that as well?
Yes, I think those were very interesting questions, actually. So regarding the wastewater, it's really just considered for the best systems. So we're not using it, or we're not considering it directly for the algae cultivation right now. It could maybe be a future question, but it's nothing we consider. And then for the mutagenesis, right now, I don't think we have a method for ensuring that the mutants are stable, unfortunately. And also so we just had to sort of pick those that looked promising and hope that they retain their abilities. And then for the but cultivating these mixotrophically is a very interesting case, because it turns out this Chlorella vulgaris really only increase lipid accumulation when it's stressed. So you sort of have to first let them grow to a very dense culture, and then you have to stress them. And this we haven't figured out, this cultivation regime yet.
Mm-hmm. Yes, thank you. Thank you very much.
Next speaker, no, yes, is Professor Dimitros Malamis. The floor is yours.
I think this is...
Present the Kronos project.
Yes. Hello again. We had some technical issues, but okay, I think this is the right one. This is the right presentation. My name is Dimitris Malamis. I'm the project coordinator of Horizon Project Kronos. Thank you very much for the opportunity that you give me to present the work. Kronos actually is a Horizon project. Stands for capture and reuse of biogenic gases for negative emissions, sustainable biofuels. It's a real project, started in 2022, and it ends up actually this year, 2026. We've got 13 partners across Europe and the UK. They do have a combined, I would say, expertise from universities, NGOs, research centers, SMEs. And our overall goal is actually to support sustainable bioenergy by integrating carbon capture, utilization, and storage into the biofuels and bioenergy value chain. So what Kronos actually aims to address is carbon waste and biogenic gases from biofuel and bioenergy production. And in order to address this, we've developed, and we're actually testing 5 functional prototypes, 5 different technological processes that we aim to enable efficient capture, utilization, and storage of biogenic CO2. But why focus on biogenic CO2? Unlike CO2 from fossil fuels, biogenic CO2 is part of the natural carbon cycle, as you see from this slide. And plants actually absorb CO2, they grow, and when we process biomass, the same CO2 is released to the environment. So it doesn't actually increase the net emissions. And that is, I think, what makes bio-based systems like Kronos promising. So if we capture actually this biogenic CO2, we can go beyond the zero emissions. We can go to territories which are actually carbon negative. And here, as you see, we aim to tackle, I said, biogenic CO2 coming from different processes, processes like combustion, ethanolic fermentation, anaerobic digestion, pyrolysis. We do have CO2, biogenic CO2 emitted from this biomass process. So we eventually, using alternative biological, technological, I would say, pathways like CO2 capture, enzymatic capture for algae cultivation. We use microbial electrolysis cells, biological CO2 hydrogenation, syngas biomethanation, all of which are different processes that have an aim to actually produce carbon-based products, like algae biomass, biomethane, even biochar. The project has 7 specific objectives, all of which are very much connected to the different work packages involved in Kronos project. So in this presentation, I will just mention a few words about each of these objectives and eventually some outputs that we have from the implementation of Kronos. So this slide here shows essentially a mapping of the biogenic gas sources across European countries. And we have identified these plants, I would say so far, which are listed more than 18,000 plants that operate across EU. And most of these, as you see from the right-hand side, are basically biomethane and biogas plants. However, we also identified other bioenergy plants for like biochar production, syngas production, combustion processes, as well as bioethanol production. Germany and Sweden are the leaders in this case in the production or in operation of these plants, and this is actually very much linked to the production of also biogenic CO2 capture, which what we're seeing is that there are very limited plants that actually operate when it comes to the capture, carbon capture and utilization or storage of CO2. And our next objective has to do with how we actually engage with society in order to involve them in the process of Kronos. So we've developed the so-called community of practices in order to co-design, co-develop, and co-implement the Kronos pathways that are foreseen in our project. Different meetings with different, I would say, thematics in order to make sure that we engage in an appropriate way all the different, let's say, groups like industry, research, governance, and civil society. So this is a pathway, I would say, of how society will actually accept the solutions that we propose in our project. Objective 3, I would say this is the more ambitious, more challenging objective to achieve. You see in this slide the 5 different functional prototypes, the different pilots that we've developed. But before developing these pilots, we also perform lab testing of the different technological solutions in order to determine the optimum conditions to which will be applied, which actually have been applied in each functional prototype. So we had to design them, we had to develop them, we had to install them and operate them. In the next slides, I'm going to give a few more information for each functional prototype, but keep in mind that after this session, we do have a specific session for Kronos in Ialisos room at 3 o'clock. If you want to participate and get more information about the operation and some results from each functional prototype. First one is the functional prototype operating in Athens, in Greece, at the Lavrio Technological and Cultural Park. The idea is, do we have a pointer? It's difficult to operate, but okay. At the bottom, you see a biorefinery, who actually treats different sources of biomass in order to extract bioethanol, bio-oils, depending on the characteristics of the biomass that we treat. And residues end up in an aerobic digester. The idea is that this biorefinery produces essentially CO2 and biogenic gases, which in Kronos we aim to dissolve and feed an algae pond in order to get algae biomass. So this is pretty much the idea behind FP1. FP2, functional prototype 2 in Thessaloniki, Greece, operated by Elgo Dimitra. The idea here is to apply a process called biological CO2 hydrogenation, meaning that CO2 combined with hydrogen can give us methane. Okay, so the, sorry, what did I press? Okay, wrong button. So the idea, we get the CO2 from the biogas resulting from an anaerobic digester, and it's fed to the treatment filter biomethanol reactor. And we supply also hydrogen from water pyrolysis using surplus renewable electricity. So we get actually biomethane. Biomethane actually has more than 95% of methane to be fed essentially to the natural grid. FP3 is being operated by DTU. The idea here is to apply a process called syngas biomethanation. So syngas results from a pyrolysis process of the solid part of the anaerobic digester unit. So this syngas essentially is fed to a biomethanation reactor in order, along with hydrogen from an external source, in order to produce, again, biomethane. FP4. The idea here is, and this is actually a functional prototype which is very much linked to the previous one. This is to operate a pyrolysis unit using different sources of biomass. Biochar is essentially produced in order to be used for testing and testing against of the agronomic performance of the material, and of course to test the syngas resulting from the pyrolysis unit, which, as said, this can be fed to the, has the potential to be fed to the previous functional prototype to produce biomethane. The last one is operated by Cartif, our Spanish partner. It's a process called in situ biomethanation using microbial electrolysis cells. The idea is to put this technology inside an anaerobic digester and enhance the process of methane production by essentially converting part of the CO2 into methane. So enriching essentially the biogas in methane content. As all projects, the same applies to Kronos. We need to assess our findings and our technologies against the environmental circularity, economic as well as social impact. So we use a range of different tools in order to determine the sustainability level of each of the proposed systems and technologies. But a crucial thing I would say here is how we actually integrate this. We integrate all the different tools in order to get a final decision support system. So currently we're in the development of such a system that will be able to use all this different information coming from the different tools, using the different data from our FP technologies to be able to provide some sort of decision-making, supporting decision-making when it comes to the different pathways for biogenic CO2 valorization. In terms of market uptake, again, here, this is horizontal activities, as you know. We've developed the exploitation scenarios, the business models are in stage, I would say, in finalization stage, more or less. And we also have a presentation today in the session I've mentioned earlier, when more information about the market uptake of these technologies will be presented. Based on the information we got, another important, I would say, objective is how we actually translate all this scientific information into some sort of brushless language to be understood by the policymakers. So we've developed a policy brief, an initial one, when we actually determine the barriers, technological, economical, as well as regulatory barriers. I think it's a good piece of document there that identifies essential elements to be considered. And we expect by the end of the project to also have a second policy brief to integrate all the remaining essential, I would say, information from the project, from its operation, from the sustainability aspect, to be integrated in the final document to be communicated. You can use all these links and QR codes to have access to our social media and our website if you're interested in following our project. And yeah, that was it. Stay connected. I think we've got the last mile now to present the most essential, I would say, findings of Kronos project. I don't know whether I was in time, but...
Yes, we have time for one question. Yes.
Thank you for the nice presentation, a very beautiful project. Only a curiosity, from the techno-economical point of view, which kind of tool you used?
You mean the market,
for
market
the assessment, for the assessment of the techno-economic?
As said, we do use many different tools. We have techno-economic assessments, we have life cycle assessment, we have carbon perspective.
Yes, from the economical point of view, for the assessment of the economical characteristic, which kind of tool you use it? Because for the LCA, you use the ISO standard. Yeah. For the techno-economical?
You will have more information in the next session about the methodology specifically. We have developed the exploitation results so far. We've had discussion with a group who is responsible for essentially delivering the business plans at the end of the project, of course. So we've had each technical team, each functional prototype operator communicated all the technical information in order to deliver the exploitation scenarios. Of course, there was also integration of this, what we call the community of practices, in order to consider elements that are important from different stakeholders. And once we had these exploitation results, there was some sort of a preliminary market analysis as well. We haven't defined it yet. We don't have the final, let's say, report to be presented yet, but we do have some information that can be presented at the next session with more details about each of these functional prototypes.
And maybe continue the conversation in the other session as well,
sure.
Because we're slightly late. Yeah, sorry.
Thank you.
Yeah, thank you very much. Thank you, Dimitri. And now we have our last but not the least presentation about the Icarus project. It will be given by Lucas Gabriel, or no? Yeah, Lucas Gabriel from CRES, I guess. Yes, okay. So the floor is yours. Thank you.
Hello, my name is Lucas Gabriel. I'm working in CRES, Center for Renewable Energy Sources, and I'm going to make a presentation about Project Icarus that we are working on it these days. The Icarus project is investigating aspects related to sustainable aviation biofuels. The objectives of the project is to develop best practices and concepts based on three most promising pathways for producing SAF, sustainable aviation fuel, in Europe and mission innovation countries, considering the technical feasibility, economic viability, and environmental impact. The three pathways that are investigated in Icarus project are, except HEFA, which is the most well-established pathway now for production of SAF, is the hydrothermal liquefaction of biomass and of different biomass feedstocks. The other pathway is the production of isobutanol, again from different biomass feedstocks. And the third one is the gasification of biomass. All of them, after the initial production, they will receive a secondary treatment to end up to SAF, to a liquid fuel that has the quality to be characterized as SAF. In Icarus project, it's an International Horizon Europe project. Its duration was 36 months. It is finishing by the end of the year, of this year. There are 15 European partners participating in it from 9 different countries. There are 5 partners from the 3 mission innovation countries, from Canada, Brazil, and India. Now, why the investigation of SAF production is important? 23% of the global CO2 emissions coming from transportation. As we can see, is the third biggest source of CO2. Within this transportation sector, there are a lot of measures have taken that manage to reduce these emissions. In the only part of this sector that there is an increase in the emission is the air travel. That's why the cause of that is that still there is not a reliable alternative biofuel to be used in air travel, in aviation travel. Now, based on that, IATA, which is the international organization for airlines, has committed to reach by 2050 in almost net zero emission flights. It's a very ambitious target. And if we take it into consideration, what is the situation now? As we can see, now only 129 million tons of CO2 are reduced in the aviation industry, and this reduction usually takes place by using other measures, indirect measures, and not by changing the fuel that is used in the aviation industry. According to the IATA, in order to achieve this target, 65% of the aviation fuel must be sustainable fuel in 2050. Also, another issue that is very important, especially for Europe, is the dependency from fuels that are coming outside Europe. As we can see now, most of the aviation fuel used in EU is coming from the Middle East, Kuwait, United Arab Emirates, and Saudi Arabia. These are products that are coming already distilled, ready to use. In the second chart, we can see that 1/3 of the aviation fuel used in Greece, in Europe, is coming as a distilled product, ready-made product, and 2/3 of it is coming from as crude oil, and it's been processed in Europe. As we can see there is only a very tiny percentage of crude oil produced in Europe, and all other sources are outside Europe. So for fuel security, it's very important as well to have a European source for aviation fuel. This is the project. This is what is expected to happen in the market in SAF. As we can see now, most of the SAF that is used is produced by the HEFA method, as we said. Is the only well-established method that is present now. The problem with HEFA is that it's relied a lot on used oils in order the end product to be characterized as SAF. So there is a need to find different sources and different pathways in order to produce SAF. And according to the studies of IATA, these sources, the most promising sources is gasification and Fischer-Tropsch in order to produce SAF at the end. And then is alcohol to jet. That means production of alcohol, and from alcohol then to produce SAF. At the end, in 2050, the biggest portion of SAF production is expected to be powered. It's from power to liquid method. That means there will be usage of electricity, captured carbon from captured CO2, and renewable hydrogen, and this will be the method that will produce the major part of SAF used in 2050. As we said in the beginning, in Icarus project, there are three pathways that are investigated. The first one, it was the production of bio-oils using different biomass sources like sludges, municipal solid waste, or algae. This feedstock undergoes under a pretreatment stage, mainly to remove nitrogen. Then they undergoes under the hydrothermal liquefaction process, and further they had a secondary treatment stage in order to become to attain the quality of SAF. The innovations that are developed within Icarus projects is the improvement of feedstock pretreatment, and as we said, mainly to reduce nitrogen, and secondary, the creation of an innovative catalyst to help the hydrothermal liquefaction process and simplify the afterwards hydrotreatment process at the end. This is the value chain, schematically the value chain of the first pathway is we are focused on non-food biomass, which is a major issue regarding the feedstock that we have to find and use, and mainly we are focused on microalgae usage. Then this microalgae undergoes other pretreatment to remove nitrogen and salt and improve the feedstock quality. Then there is the feedstock undergoes the hydrothermal liquefaction process, which enables the use of wet biomass. That's an advantage because we skip the drying step, which is energy consuming. And then we upgrade with the hydro treatment process the product coming out from the hydrothermal liquefaction. Finally, we reach the quality of SAF and comply with the standards of HTM that you have to do it in order to have a commercial product. As we can see, the operating condition of the hydrothermal liquefaction process, the operating conditions are, it took place in the absence of oxygen or air. The used temperature is about, it's between 200 and 375 degrees in high pressure, in 100 to 250 bars, and with small residence time. The output from the process is a bio-oil, are gaseous products, and biochar. The problem is that the bio-oil produced from this process, if we compare it with conventional oil, by crude oil, it has lower high heating value, it has lower concentration of hydrogen, of carbon, but higher concentration of oxygen and nitrogen, which is not something that we like. That's why we have to go to a second stage of treatment, which is the hydrodeoxygenation stage, where this bio-oil undergoes into a reaction that hydrogen is added and oxygen is removed. This reaction took place at almost similar temperature, about 200, from 200 to 400 degrees. The pressure is lower, to 20 to 100 bar, and there is a usage of catalysts. This is the area where Icarus was doing research in order to to create a catalyst, a proper catalyst for this reaction. The product of this reaction, the products of this process are gases, water, and hydrocarbons, which then can be fractionized like a distillation process, conventional distillation process, and took the useful part that can be characterized as SAF. The second pathway is the production of isobutanol. Target of this pathway is to use agro and forest residues. That means, 1 minute, that means solid state lignocellulosic biomass. And the objective is to generate a special yeast that can convert this biomass to isobutanol, which then can be converted to SAF. I'm not saying a lot of details. The third one, it was a typical gasification process that can use lignocellulosic biomass. Through the gasification process, the syngas produced, which is carbon monoxide and hydrogen, can be either through Fischer-Tropsch reaction end up to liquid fuel, or can be converted to methanol, and this methanol end up to liquid fuel, or the third solution that is investigated within the Icarus project. It was a modified Fischer-Tropsch reaction. Instead of producing small organic molecules, produce olefins, which is larger, and then through an oligomerization process, produce the chain, the carbon chain that we want in order to have SAF at the end. This is the description, more detailed description of this process, and in order to conclude, the results from the Icarus project so far is that it's obligatory to have different pathways in order to achieve the SAF targets for 2050. Icarus is investigating 3 different pathways instead of the well-established HEFA method, and especially regarding the biocrude pathway, is working on feedstock pretreatment and development of new catalysts.
Yeah, we could